Welcome to the sixth problem solving session for Introduction to Semiconductor Devices with code NOC 23E82, hosted by NPTEL, and the lecturer is Professor Naresh from IIT Hyderabad. This is week 6 on September 2nd, 2023, and my name is Amit. I am a PhD scholar at ISC Bangalore. So in the previous sessions, in the first session we talked about the material classification, and primarily in terms of conductivity. We saw that semiconductors have conductivity in between metals and non-metals, and its primary property being that conductivity can be tuned. And we saw some basics of quantum mechanics like de Broglie wavelength. This is where all those quantum mechanical effects come into the picture, and then Heisenberg uncertainty principle. We saw infinite quantum wells, that is something like this. So on the y-axis you have a potential, on the x-axis you have position, let's say, and this is a well. So this tends to infinity, v equal to infinity, and we saw that a particle that is here, it's confined, and we saw that energy is quantized. In the classical world we see energy as continuum, but here energy is quantized. Only certain levels of energy are allowed. We also saw this is an asymmetric quantum well from 0 to L. Symmetric one will be that is from minus L to L. The wave functions will change accordingly. And again, a very unique property of quantum mechanics, we saw that, let's say, again, your y-axis is your potential and x-axis is your position. So let's say some particle is coming from this direction, and it has to cross this barrier, so v equal to v naught. We know classically that this particle can never breach, can never come to this side, but quantum mechanically we saw there is some finite probability of finding the particle here also, since it went across a barrier. This is also known as quantum tunneling. Coming back to the semiconductors, we saw how this quantum mechanical effects, like Ronick-Penny model and certain assumptions that we made of periodicity, gave that overlapping of orbitals, and then finally the origin of band gap. By band gap we mean that there is an conduction band, so electrons can reside above the conduction band and below the valence band, but an electron is not allowed to have this energy, somewhere in between. That's why it's called also known as forbidden energy. We also saw that we can excite the electron from valence band to conduction band, right? How we can do that? Through by shining light or by increasing temperature, where the bonds will break of the constituent atoms. So second week we saw the effective mass and it's a link to dispersion relation. Dispersion relation is EK. E is energy, K is your wave vector, right? And then we saw that there is a curvature in conduction. I'm drawing them flat, but actually they're not flat. If you draw the EK diagram, you'll see there is a curvature which gives rise to an effective mass, and the effective mass we saw was a very important quantity in the sense that all the quantum mechanical effects are condensed into this effective mass. So we need not worry about quantum mechanics to most extent, and we just, wherever m comes, we replace with m star. So m star, this is how it's depicted, effective mass. Then we saw that in a semiconductor we can dope them. Dope means adding some impurities. So you can add impurities which can donate electrons, which will make semiconductor n-type, and you can also donate impurities which can accept electrons, and thus making the material as a whole slightly p-type. Closely linked to that was the Fermi level, where the probability of finding an electron is half exactly. We saw its position in the band gap and how it changes when we dope it n-type and p-type. Finally, we saw some carrier concentrations in equilibrium, and these are some constants Nc and Nv that you see here that depend on the material and the temperature. Ni is important parameter. It's the intrinsic concentration. So for instance, Ni for electron is 1.5 10 to the power 10 cm minus 3 at room temperature, again 300 Kelvin. Cm minus 3, we saw that we tend to choose units in terms of centimeters, not meters, the SI metric, that is. Finally, we saw the carrier concentration on temperature, how at low temperatures the ions, the dopants that you have put in the semiconductor, they're not fully ionized, so they are not contributing as much. Then there comes a regime called the extrinsic regime, where all the electrons, all the dopants have been ionized. That means they have made the material n-type as much as they can, or p-type, depending on whether they're donor or acceptors. And finally, if we increase the temperature even further, then the bonds will start to break of the inherent semiconductor, and we see a huge increase in concentration of electrons as well as holes. Week 3 we saw non-uniform doping. That is when we see the valence and conduction bands are not flat, they can be tilted, right? And corresponding to this, they will have an electric field, because this is potential, and we know electric field is minus grad V, right? So we saw that, and this means there is a built-in electric field and associated kinetic energy. Then we saw the two important components of electrons. Okay, electrons are present. What are they doing? They can carry current. How? Something called drift current, that is when the electrons are moving or charge carriers are moving in presence of electric field. And closely concepts for mobility denoted by mu and conductivity denoted by sigma, right? And then diffusion, because if there's concentration electrons more on one side, less on other side, then they can diffuse from one side to other. We saw there's a diffusion current related to that, and we also saw that by the Einstein relation, the mobility and diffusion are linked to each other, right? So d my mu equal to kt by q, something like that. We saw an expression, right? Moving further, what we saw was that that when we disturb the equilibrium, how we inject some carriers, that is apply a voltage, or you shine light, and which will generate electron hole pairs, and they can recombine also, right? They can always recombine, but that means that it's not no more at equilibrium. And based on this understanding, we saw something called minority carrier diffusion equation, which encompasses all of these considerations like generation, injection, low level injection, diffusion, drift, and everything. Finally, we saw, based on equipped with now all the basic knowledge of a semiconductor, now we brought a p-type semiconductor, n-type semiconductor together, and we saw how a depletion region is formed in a p-n junction. Primarily we are interested in abrupt or step p-n junction, but there are different flavors like pin, pn plus, this means n is highly doped and p is moderately doped. We saw depletion approximation to solve the Poisson's equation, and the quasi-neutral region was again an approximation that was taken. The terms and the expressions that you saw were depletion width, the peak electric field, the stored charge, and the built-in potential. Whenever there is a field, there will be a potential. Just keep that in mind. It's very handy. Finally, from the last session, we saw what are quasi-Fermi levels. That means that the p-n junction is no more at equilibrium. What will happen? The way to disturb is that in order to understand, we introduce something called quasi-Fermi levels. So by that I mean like this. This is EC and this is EV. Usually we draw only one Fermi level like this, EF. But when there is injection of carriers, this is at equilibrium. This is at equilibrium. When it's not an equilibrium, we draw something like this. So this is EC. We call this EFN, and this is EV, right? And let me draw EFP with a different color just to illustrate. So in this, when there's injection of carriers, this is EFP. This is different. This is no more at equilibrium. There is some injection or generation of carriers. And we saw those expressions and whatnot. Finally, we saw that when we inject the carriers, the potential barrier, that is, we have been seeing this diagram, right? This is the built-in potential in a PN diode. So this gets lower. This means this gets shifted a bit towards the upside. That means potential barrier lowering. And we saw now the carriers which are here now can diffuse to this side, which can contribute to the current. And obviously once they diffuse to this side, that is the electrons, they'll recombine, right? The total current has to remain constant. We also saw that under reverse bias, different thing will happen. That means, which is in this now bright red color, that in this is for reverse bias, this will widen and thus no more current can take place. However, we saw that if some minority carriers are able to reach in this depletion region now, which is widened, by the way, this region is the depletion region, this will get widened in reverse bias. We saw that, and the potential barrier will increase. But there is a drift. If some carriers too are able to come here, they are quickly swept away due to the very large electric field that is present in this widened depletion region. Finally, we saw something called a junction capacitance and its dependence on reverse bias and doping. And we also saw one very particular example where one side of the p junction is completely depleted. This means such high reverse bias was applied. So I'll take a pause here, and so till now we have, this is just the summary of previous 5 sessions. Now what we'll do, we'll from the PN junctions, is a different flavor of another junction, right? Please remember, in P, this was a P-type block, this was an N-type block. We brought them together to form something like this, PN. Remember, this was what we call the metallurgical junction, right? So till now we have talked about that. So basics of semiconductor will still apply. But now, instead of a PN junction, what we'll have is something different, which we'll see in today's session. So before I start, let me take a pause, and if you have any doubts till now in the basics, just feel free to ask. Otherwise, we can get started. All right. Okay, let's get going from this session. Now, I hope you would have seen the videos, right? So this is a question, this is very basic, fundamental question. Which one of the following is the work function? So in order to understand that, we draw this diagram, right? So this is a metal, as you can see, and this something we draw some vacuum level. This means the at vacuum electron will have some energy. Call it E vacuum. Okay. The work function for any material is something the energy required that to move an electron from this Fermi level, you can see EF here, to the vacuum level till here. So whatever this energy is, it's called the work function of that material. So in this case, it's a metal here that I have drawn. So when you move an electron from metal, okay, by the way, in metal, Fermi level is something, the level at which it's completely filled. So you see this dashed line, this means electrons are available at energy EF and just below. Below is obviously filled, so energy electrons are available. So maximum available energy is EF in a metal. And so what is the energy required to reach to make it go to the vacuum level? That is what is known as the work function. So it's phi m is usually denoted in terms of volts, right? And please remember, we are plotting potential energies here, hence you see this multiplication by an E Q charge. So charge into voltage is nothing but your potential energy. All right, so the answer here would be the work function is nothing but energy required to move an electron from EF to vacuum level, EF to vacuum level. So this will be your correct response. A similar understanding is we need to have is of electron affinity. Affinity means closeness, fondness, right? So what is that? So in this case, this is a semiconductor that I have drawn. This is from your lecture slides only. This is a semiconductor. You can see it's a N-type semiconductor because Fermi level is close to the conduction band. All right, this is an N-type semiconductor. N-type semiconductor. Very good. So again, you see the symbol phi s. This is nothing but the work function again. So work function for this N-type semiconductor is this. That is the energy required to move an electron from EF to E0, the vacuum level. All right. What is electron affinity? Now please note that the electrons will not be residing here in an ideal N-type semiconductor. Remember, this gap is what is the forbidden gap. So in semiconductors, work function is more of a theoretical construct in an ideal world, but we'll see hopefully that sometimes some states are there even in between. All right, let's forget about that. Chi, the symbol chi that you see is the difference between EC and E naught. Please remember, electrons can reside here for semiconductor, right? So the energy required to excite an electron from EC to vacuum level is what is known as the electron affinity. So EC to vacuum level, this means this option. All right, so these two are some basic definitions that that I felt important to visit, just to remind you. Now let's go ahead with today's first major topic. Okay, right. So this is Schottky junction. So what is a Schottky junction? So Schottky junction is nothing but the interface between a metal and a semiconductor. Recall, PN junction was between two semiconductors, P-type and N-type. Schottky junction is between a metal and a semiconductor. So here we have, this means we are they are not in physical contact yet. So you see, metal is, it's all the properties, it's here, it's filled till EF, and this is the work function that we have. On the other hand, this is the semiconductor, as we saw, this is the N-type one, because EF is close to EC. And again, you see this phi s work function of the semiconductor, chi the electron affinity for this semiconductor. Now, when they are brought together, you know that in equilibrium, that means no bias, no shining light, etc., EF should be flat for this complete system. So before contact, this is the picture. After contact, you see that this EF is higher, right? So what will happen? This means electrons have more energy here. So electrons will try to go this side, right? If electrons will try to go this side, this means they will leave a positive charge. Remember, this is doped. Then the depletion region will form, and the new picture will look something like this. You can see this depletion region. So here, this is positively charged. These are lattice ions that have been left behind. All right, throughout. And you can see the EF is flat now. EF is flat. This means that equilibrium has been achieved. Now, you can see a depletion region, and you can see also the bending of the bands. Now, naturally, there will be electric field that is involved. And again, the bending of the bands is what we refer to as the built-in potential, just like in PN junctions. We'll see a comparison on later also. But again, this this facet that you see, EVBI, is nothing but the built-in potential. There's another entity called phi B0. This is called the barrier. So just imagine if some electron wants to travel from this metal to this semiconductor, right? We saw that in I just talked about the quantum tunneling. So what can happen is that it can tunnel through this, but usually this tunneling happens at very low widths. We are talking about few nanometers. Depletion widths usually that we see are few microns, right? So it cannot tunnel through, so it has to go above something like this, right? Hence this is called a barrier, and since this is named after Mr. Schottky, so then this is called the Schottky barrier. So again, phi B0 is the Schottky barrier in a metal semiconductor junction. Again, VBI is the built-in potential, phi B0 is the Schottky barrier, and you see this phi n, this is the difference between EC and EF. We have been seeing this, right, multiple times. There's multiple expressions like n equal to nc e raised to the power e raised to exponential of minus EC minus EF over KT in those expressions. So this is a new entity, but we have been seeing that. It's just that we are naming it right now. All right, so these are the constructs that you should keep in mind. Now, there's a question related to that. It says that given below are two statements regarding Schottky diodes. So Schottky diodes are nothing but when you make a Schottky contact, right? So you have this like a PN junction, and corresponding device is called a PN diode. Similarly, this is Schottky junction or Metal-Semiconductor Junction, and the consequent device is what we call a Schottky diode, right? The question asks that there's two statements and we need to find the true and false of them. So it says that S1 says that Schottky diodes are majority carrier devices. So what do we mean by that? So let's look at this picture now. On the left you have a PN junction, an abrupt PN junction, step PN junction. On the right side you have a Schottky. All right, so we saw that in this picture, if you recall, in the last session we had the electron current contribution as well as the hole current, right? So both of them were contributing to the current that is flowing. So there was diffusion and drift of both of these entities in case we applied a forward bias. This is in a PN junction. However, if you see here, there are electrons here, so electrons see this barrier, but for holes, I mean, you cannot see the availability of holes, for instance, in this picture, at least in this metal, right? So what's going to happen, that's why in this type of semiconductor, right, this is because it's a metal N type, there's only one carriers, so it is only electrons that are carriers. The holes will not carry current, so electron is the carrier, current carrier, that is, and electrons are in majority here. This is N type, right? So hence we see that in Schottky junctions these are majority carrier devices. So statement S1 is true. So this statement is true. Let's look at the second statement now. Schottky diodes switching speeds are much more than PN diodes. For this we need to understand a bit about the PN diodes, for instance, right? So let's say when I'm applying forward bias, we know in the forward bias the picture will look something like this. I'm just redrawing this in the green, right? This is the green line is after the forward bias. So this is, let's say, VBI minus VA, a forward bias. What will happen in forward bias? We see now, since the barrier is lowered, electrons can go from left to right. Holes can go from left to right, and the electrons will go from right to left. We have seen that in the previous class. So what happens? Let's say I switch off the I change the polarity all of a sudden. So what's going to happen, which I now will show in blue. What's going to happen is that this barrier we know is going to extend further, something like this. So this is VBI plus VR correspondingly here. So this barrier will also increase on the valence band side, right? So this barrier is now VBI plus VR, this entity, and blue is your reverse bias. In reverse bias, we know that there are no free carriers. So whatever, so assume that some current in the, when you are in the forward bias in the green regime, there are electrons and holes in this depletion region. You remember that, right? Because they are traversing. All of a sudden, if you now change the polarity in the depletion region, what will happen to all the electrons and holes which are trapped in this region? They have to be evacuated. They have to be evacuated by this reverse bias electric field that's linked to reverse bias. Okay, so it takes some time. It takes some time for the electrons and holes which are present here in the forward bias to get cleared, to get empty, because this has to be devoid of free carriers. Remember that. That term is something called reverse recovery time. That, as it happens, because you can see they have to be cleared across the depletion width, that takes much more time as compared to a Schottky diode, because first of all there is only one carrier that is to be removed, and electrons usually have much higher mobility, right, than holes, because holes, you see, are the vacancies, so inherently they are slower. So in that sense, due to the fact that especially when electron is the majority charge carrier, the Schottky diodes have much faster switching speeds. So switching speeds means on and off. How long does it take? How many microseconds or nanoseconds? And then to on again, right? This is switching. This is first switching and this is the switching, second switching. How long does it take? For diodes, it takes much more time because it's reverse recovery time. That means the time for which the carriers to get cleared is much higher. This is one of the explanations, simplistic one that I'm giving you. So we see that second statement is also true. Okay, and it's a direct consequence of statement 1. So this will be the correct option. I'll repeat, statement S1 is true because we see that the electrons are the majority charge carriers in this. For instance, we see when we apply a bias, this barrier will get lowered, just like in PN diode, right? But PN diode, both electron and hole contribute to the current. In this, only the electrons are the charge carriers. Okay. On the other hand, about S2, the reverse recovery time is much smaller, among other reasons, since there is no in the depletion region, there are much lower carriers to be cleared, or the mobility is higher. There are different ways of looking at it. Hence S2 the S2 will also be true. The statement 2 will also be true, and it's a consequence of the first statement. So I hope that answers the questions. I'll take a pause here, and just if you have any comments or questions, you may ask.
Sir, will junction capacitance play a role in delay?
Yes, you can. So there are, again, as I was saying, there are different ways of looking at it. So what I was explaining in terms of carriers, right? The second thing is you can look at in terms of is the junction capacitance. A junction capacitance, so usually we associated junction capacitance with the reverse bias. If you recall, in the forward bias there's something called a diffusion capacitance, because in the forward bias, so in a PN junction diode, it will see in the forward bias diffusion capacitance, in the reverse bias it's a junction capacitance. Junction capacitance, why did it arise? If you recall, it arose because of the fact that there are some charge carriers, right, between on the both sides of metallurgical junction, and we assumed it, and we tried to replicate it, just like, oh, it's a capacitor, positive and negative currents separated by each other, which are fixed in lattice. So we assumed that system, we simplified it in for our understanding to be a capacitance, right? So you can look at it that way also. It's just a different way of looking at it, right? Rather than through looking from the perspective of charge carriers or charges, you're looking in terms of an electrical device, which is a capacitor in this case. So yeah, you're correct. You can look it from that perspective. Yeah.
Sir, in PN junction there are two capacitance, and in metal semiconductor only one capacitance. So sir, how we compare both of them?
No, there is a two. So see, again, you have to understand that capacitance is arising due to the distribution of charges. So as I told you in some previous slide, I had shown that there are some charges here because this region is depleted, right? And if you recall your electrostatics, there is something called a mirror charge. Okay, there is a mirror charge that appears when a metal makes interface with some dielectric. Assume this to be a dielectric now for this understanding. There is a mirror charge, that a negative charge appears here. So again, in this case, what we'll do is that we'll assume this to be something like a P plus N. It's, again, I repeat, it's not a PN junction. It's something like that. The depletion width is 0 in the metal, and it's extending somewhat in the semiconductor. It's completely in the semiconductor. So assume it like that. Okay, just think of this metal as a p type, p plus, highly doped p, and on the other side you have a moderately doped n side semiconductor. And now you can, whatever understanding you have of p-n junctions in terms of capacitance, that is, or the peak electric field or the built-in potential, we'll see again one more comparison where the understanding or the expressions that we have for a p-n junction diode, we take them directly over here in Schottky junctions. But the methodology, the way current is being transported, is completely different. In the p-n junctions forward bias, it's through diffusion. We saw p-n junction reverse bias, it's through drift. In this case, it's something called a thermionic emission, which I hope is, yeah, there's a slide somewhere. We'll come to that, don't worry about it. But there is a capacitance involved here also. So when you apply a forward bias, so this will shrink, right? The built-in effective built-in potential, this line will go up, just like was in forward diode. So this, again, this green line is for forward, right? And similarly, if you apply a reverse bias, so this will come down. So depletion width will increase. So this is, sorry, this is not, I meant to say reverse bias. Just a second. Yeah, so this is what I meant. When you apply a reverse bias, this will come down and depletion width will widen, just like we had in p-n junction. So for that perspective, if you are comfortable with that thing, that what about depletion regions and my built-in potential, if you are comfortable with expressions, the understanding in terms of expressions, then think of this junction as a p plus n junction, and that will help. Those are the expressions that you can directly carry forward, except that on the metal side you assume it to be highly doped. So all the depletion and all the electric field will be dropped only in the semiconductor. So that's the only difference. Capacitance will still be there. You just call it with a different name, because this diffusion is not happening here. We just call it the, let's say, the capacitance of this junction. All right, does that answer your question?
Yes, sir.
Okay, all right. That was a good doubt that you asked, because it's sometimes very basic that what is the difference. Even we can see that it's a metal and semiconductor, fine, but how it's related to p-n junction. So that's for just for the starting, for understanding, assume it to be a p plus n. It's not p plus n, but I'm saying in terms of expressions it's similar to that. All right, and that is what I was coming to. So where does a peak electric field occur in a metal semiconductor junction? So as I told you, in a metal semiconductor junction, assume it to be like something like p plus n. All right, and as we saw, so I'm going to draw some so this is the electric field. We saw that in p plus n, if you recall, the diagram looks something like this. So this is the p side, p plus slide, this is the n side. On the y-axis we have electric field, this is along the x-axis, and let me just, for the sake of completion, let me draw the, so this is p plus and this is n, and this is your depletion width, something like this. So depletion width is in the dashed lines that you see. I'll draw again. So left side is p plus, right side is n, and this is your, so you can see almost all the depletion is dropping here, right? And this will be positively charged. Those all things remain, but again the peak will happen at the interface, at the junction of p plus n. This is a p plus n, but I'm asking you is to just assume that Schottky junction for this specific understanding of how the electric field looks, it's very similar to what happens in a p plus n junction, right? So here again we saw that it's happening at the metallurgical junction. So in this case we call it the metal-semiconductor interface, right, or metal-semiconductor junction. This is also a junction, it's not like, so that's how we do. So if you see that, so what we do is that this is an n-type semiconductor, this is a planar picture, and what we do is that we just implant metal here. So this is the metal, right? So what you have, that's I'm doing how we do in fabrication. I think there are some lectures according to that. So you see this thing in blue, this becomes your metal semiconductor interface. So here will be the peak electric field, just like in a p-n junction. All right. So now we'll quickly, whatever basic understanding that we have for metal semiconductor junction, right? We'll just now, there'll be no for starters there'll be no numericals. We'll just try to understand just by seeing the band diagrams how it looks like. All right. So let me get started. So just keep in your mind your concepts regarding your PN junctions, right? Like there's built-in. So let me just let's just start with this question. I'll introduce all the concepts one by one which we had in PN junction, and that might make a bit easy for to understand. All right. So the question says that consider the equilibrium band energy diagram for an ideal. We'll see this ideality plays a very big role actually. For theoretical purposes we'll take it ideal, but when you actually fabricate these junctions, there's no more ideal. There are impurities, there are traps, there are many other things that come into place. So we are required to observe these band diagrams and answer the following questions. So the first question is, the contact is between metal and, so on one side metal is given, on the right side we need to identify what is it. So it's a p type, n type, intrinsic, insulator, or 2D material. All right. So we are not talking about 2D materials here. It can be a 2D material. They also have band gaps, but for all practical purposes, let's just ignore the last option. Is it an insulator? We don't know that, because remember, this is the EG, right? And we saw that for EG, for insulators, remember the first session, is higher than band gap of semiconductors. And there are some other peculiar properties of insulators that come into play, right? Here again, actually it's been given in the problem itself with some semiconductor junction, but for insulator we'll just ignore this. The bands gap is usually so large that they don't even make good metal semiconductor. There are some exceptions, but usually they're not there. Okay, they're not there for all practical purposes. Now we have now left with only three options: n type, p type, or intrinsic. How do you find that? Look at the level of EF. So we see that in A2A, EF is close to EC. This is the bulk region, mind you. This is depletion is happening till here, and this is bulk. Similarly, depletion is happening till here, and this is something called what we call the bulk semiconductor. All right. So what's happening in the bulk? EF is close to EC. This means it's n-type doped. In this diagram also, EF is close to EC. This means it's n-type doped again. So for both A and B, the semiconductor that we have is an n-type semiconductor, right? And we know it's in equilibrium because EF is flat. All right. Why n-type semiconductor? EF is closer to EC than to EI. So ideally it's like at the center of the band gap if it's intrinsic. I stands for intrinsic, remember that. EF is closer to EC than to EI, hence this is an n-type semiconductor. All right, so now we know that this is an n-type semiconductor. N-type semiconductor. Okay, and again remember this is a metal semiconductor junction, so this is a depletion region between the interface and the dashed line, and this is the bulk, n-type bulk. Okay, now choose the correct option for the relation between metal and semiconductor work function for this band diagram. Okay, so what's happening is, but it's a metal and semiconductor work function. So we had, in fact we have already seen that in a way. How? So let me just, so remember that, so this is the EF, let's say, for metal. This is the metal side, right? And when they are not in contact, so this is something like EC, this is EF, and this is EV, right? So what we saw this in the first, I think third or fourth slide, where we talked about where I introduced the Schottky junctions. So this is, and again this is in reference to some vacuum level. This is E0, some vacuum level. So we saw that if EF is higher here, then what's going to happen is some electrons are going to flow from this side to this side. They leave behind some positive charge, right, which will create the depletion region. So this is the exact picture. So here electrons have left, right? If electrons have left, so you can see that this EF has to come down, right? CF has to come down, this has to go up, but this point will remain fixed. That's how it's. And in the bulk, you see how the band diagrams are drawn. In Professor Naresh has explained it in many videos. Whenever sometimes band diagram, whenever the first time in a week he introduces, he usually talks about, because it's important to learn how to draw these band diagrams. So in the bulk, you can see it has to be retain its n-type character. Hence, EF is close to EC, and EF is to be flat throughout, right? So let's assume this semiconductor has to come to the metal level, right? What we do is that at junction we fix this point. This is the junction. This is the junction. So we fix this point. So this point cannot move. Similarly, this point cannot move. So these two, the large blue dots, cannot move, and this whole thing has to shift down. So what will happen? EF will remain flat. It has to remain flat because it's in equilibrium. And this is your junction again, right? These are your big two dots that I had drawn there, right? And we know this is the EF in semiconductor side, and this has to be close, right? EC has to close to EF. This is also, there has to be continuity, right? So what's going to happen? It's going to bend like this. And since EG will remain constant, remember the material is not changing. So again, till here, this will be EV, and this will go something like this. So that's how we do. Just fix these 2 points. Extend, imagine this line, just extend it to this direction. What's actually happening is electrons are flowing from here to here, and that's why I told they'll leave behind a positive charge, and hence the bends will bend in the direction that you are seeing, like this. This is the picture. So we know that this kind of picture, this kind of a metal semiconductor interface will give rise to this kind of a band diagram. So now the question asked us to compare the work functions. Remember the definition of work functions, right? Work function is between the Fermi level and the vacuum level. So this is phi m, work function of this metal. This is phi s, work function for this semiconductor, and you can see that this level is higher, right? So this means phi m has to be greater than phi s, or if phi m greater than phi s, then we get this type of a diagram. We'll see what happens in the other case shortly, but that's how the complete picture is happening. All right, so in this case we got phi m greater than phi s, so this. All right, this is the correct option. Fine. So next question is what type of contact this is. Okay, there are a few other things. So just to be, for the sake of completion, this is nothing but your barrier height, phi b, right? This is nothing but your built-in potential, because there is a bend in the, and there is a curvature in the conduction band, this is how we are defining the built-in potential, right? And consequently there will be just please understand there will always be an electric field that's associated, right? So what type of contact this is, we know it's a Schottky contact, but another term for this is the rectifying contact, because it's in some manner it's like a PN junction, right? It's used in rectifiers, hence the term rectifying comes into the picture, right? So this contact, the metal, okay, the contact, we mean the metal semiconductor contact. Okay, it's a rectifying contact because it has this nature. It has a barrier to the electron flow, and we saw that this happened because phi m was greater than phi s. Just in the previous question we saw that. Now let's consider the second picture. So now what's happening is that, again, this is the you can again see this is an n-type semiconductor. Again, I will draw just like before. So this is the depletion region in this, between the junction and the dashed line. This is your bulk type semiconductor, n-type bulk. All right, EF is close to EC in the bulk, and now we are required to find that which of these conditions, which of the relations between phi m and phi s or chi will give us this kind of contact. So again, let's do the same exercise. So we draw the vacuum level E naught, we draw EF metal. So here this is filled with electrons. This is the metal side, left side. On the right side, so let me extend this till here, and somewhere here we'll form the junction, right? So junction will be formed somewhere here. We'll draw a dotted line. They're not yet in contact, but we want them to come in contact. All right, so remember on the earlier side EF was higher here. So now let me do something like this, that EC is here and this is your EF of semiconductor, right? And this is the EV of semiconductor. Okay. Vinod, do you have a question? Because your sound, there's some disturbance coming from your side. If you don't have, thank you for muting. All right, so as I told earlier, so this is the second picture now. Now let us draw the work functions and everything again. All right, so this is phi m, remember that difference between Fermi level and the vacuum level. This will be your phi s, this will be your chi, right? And you have, I'm not drawing EG and all other things, just it will become too cluttered then. All right, so as I told, just like previous time, I'll use a different color this time. So I told you just fix these 2 points, this point and the extension of this point, just fix these two and now try to bring them close. So what will happen then? Something like this will happen. So let's, EF has to align essentially. So on the from carrier's perspective, you see this level is higher and EF is, so probability of electron is at the same, it has to, EF has to remain flat. We have to draw in equilibrium, note this word, right? So what's going to happen, electrons will jump from the metal side to semiconductor side, all right? But note, this is already n type, so a unique thing will happen now. So this is your Fermi level of the metal. All right, let's extend it this till here. This is your junction, just like before, right? And we saw that this is EC, right? Something like this. So and so this has to shift up essentially. So what's going to happen is that if EC has to shift up, this EF has to remain constant. This is EF. Essentially you're shifting this up, and in the bulk we know that EF has to be closer to EC. Similarly, this is the EV here, right? So when you shift this up, so this point will get pinned here. Made a mistake. This term will get pinned here and the bend will look something like this. Essentially this had the curvature in the previous, you saw, if this is the picture, then the curvature was downwards of EC, right? Here the conditions are different, are opposite, so curvature has to be upwards because now EF has to shift up. Similarly, again there will be a curvature like this here. Now the key thing to note is that depletion region is much smaller here, as you can see. So what's going to happen, because because electrons are not leaving the n-type semiconductor, please note that it's rich in electrons, right? They're not leaving here, right? But what's happening is that some extra electrons are being provided by the metals. So you see this region that you see here, this region is rich in electrons. And it's like EF and EC have a continuum. There's no more barriers associated. This will form a continuum like this. So the electrons, whatever is coming from this side, if you apply some potential on either side, you can lift this and then it can easily cross this barrier. If you lift this, they can from the opposite direction. This is so when this happened is that when phi m is less than phi s, this type of junction band diagram will form when phi m is less than phi s in this condition. And as I told, this type of contact, now electrons can flow freely over this regime by just application of a very small potential on either side. This is a behavior is called as the ohmic behavior. You know that, just understand it like this. So there is some black box like this. So what we do, if you apply potential like this, current flows in this direction, right? Or again the same black box, you apply the reverse polarity, current will flow in this direction. So this black box, I mean this black box is in the device that I'm talking about. This thing is behaving like an ohmic contact, ohmic behavior. This device is exhibiting ohmic behavior. Simply V equal to IR or J equal to sigma I, however you may want to prefer. It's behaving like an ohmic. This follows this relation, ohmic relation. Hence, such contacts are called ohmic contacts. And this is important for fabrication. Some contacts you want to be ohmic, right? Some contacts you want to be Schottky. That depends on what you want to achieve through those contacts. Essentially, you'll see that when MOSFET comes, we'll see these types of different flavors, right? Ohmic contact as well as Schottky contacts. This kind of behavior, essentially, since you see that this dip that you see here is fairly small to be overcome by any external applied voltage. So this now the electrons are free to roam around in this region. Not in equilibrium, but when you apply a small bias, right? Hence these such contacts are called ohmic contacts. Why they came about? This is the reason. When work function of semiconductor is greater than that of a metal. And please note that we are talking about here n-type semiconductors here. You say what happens in p-type? A different picture emerges, but essentially the concepts remain the same. We are not talking about them due to the lack of time, but in the lecture you can find that Professor Naresh does talk about them. So I request for, if you want to understand that how it's for a p-type, how it behaves, there are that's being explained, so you need not worry about that. All right, now just to sum up the picture that I've been talking about. So you see V I versus V. So you see this is a linear relation. I told you V equal to IR is your ohmic. So first is ohmic. So option, so this cannot be true, this cannot be true, this cannot be true, this cannot be true. First is ohmic. Second, we see that this is so we'll see in a while that there are some expressions that are mathematical expressions that are controlling in that how much current flows on what application of voltage. So we saw this diagram in, so diode, you can by the way, this is for a PN, this is for a Schottky, right? Why that happens is that although their forms look something very similar, like J equal to JS e to the power QVA over KT minus 1. Remember this, in fact for Schottky diode the expression remains the same. JS is the reverse saturation current, VA is nothing but your applied voltage. It just so happens that usually in Schottky junctions VA is much smaller. So VA, this is the VA, the turn on voltage or the knee voltage, different terms for them. This is the V turn on or V knee. This is for diodes. So usually for diodes it's for silicon diodes it can be 0.7 or thereabouts, right? This can be different. This can be as low as 0.2 volts even. We'll see some examples and then we'll be able to appreciate it more. The way this comes about, there's the physics that is involved is that because the nature is different. In Schottky is thermionic. Thermionic comes from thermal plus ionic, so this means it's being driven by the temperature to an extent. You will argue that in same goes for the PN junctions also, but in PN junctions, yes, it is true. I mean the concentrations do depend on temperature, but it's a diffusion of minority carriers across the depletion region. I'm only talking the forward bias, by the way. I'm not talking about reverse bias picture here, right? So that's the difference. And this the way this constant comes about, there are other terms, JS is involved here, we'll see. But for now, just take my word for this, that this is the way the carriers are behaving, right, gives rise to a different knee voltage for them both, right? And thus the correct option would be, the first is ohmic naturally, sorry, not this one, second is Schottky, the third is your PN, right? I included this because this involves an ohmic as well as a Schottky diode, Schottky junction. So you can see the comparison in the same plane, and as well as the PN junction. All right, so now till now I've been talking about all the theoretical constructs that are involved in the how a Schottky junction is formed. There's a depletion region, you saw that. But now we'll just take a step back and we'll just try to have some mathematical expressions in front of us. First, to solve the
Sir,
problems.
1 minute, sir.
Yeah, go ahead.
You have told about phi m greater than phi s and phi m less than phi s.
Yes.
So in case of phi m greater than phi s, this is ohmic or this is rectifying?
So as you see, for phi m greater than phi s, right, for phi m greater than phi s, this is rectifying. I'm talking about in terms of metal n-type semiconductor. All right, just we saw the picture like this here. So here this is the phi m on the left side, phi s is on the right side. So what's going to happen when you bring them together, so electrons will flow from semiconductor to metal because their energy is lower in the metal side, and they'll leave behind a positive charge, which creates a depletion region, which you can see in the bottom band diagram like this here. So that this picture happens only when phi m is greater than phi s. Phi m you see over here, and phi s is over here. So phi m greater than phi s will give rise to a rectifying contact, as I'm saying on this slide. Okay.
Thank you, sir.
Yeah. Okay. So and
Sir,
yeah. Go ahead.
sir, in one of them, one of the four, there is a condition where electrons are going from the p-type to metal. Is it possible?
Yes. So I mean, I know it looks very strange that how will the holes go. For from basic perspective, you have to then to understand how physically it's happening. Please recall that holes is nothing but a vacancy of an electron. So but when we draw it here, we treat hole as a particle, like as if hole is a separate entity which exists in nature just like an electron. That's not the case. It's a hole does not I mean independently does not exist. It's just a vacancy of an electron. So when we have a p-type semiconductor, again we understand them in terms of band diagrams, right? So that's how again that can happen. I don't have those slides for I think p-type, but similar situation when you have a metal and a p-type semiconductor in contact, because remember the only thing that's going to matter is the Fermi. You have to align the Fermi level, and you see just like here, and accordingly the bands will shift. Okay, and alternately you can see from in terms of as from a carrier perspective, if you're not don't feel comfortable with the band diagram, think of the carriers which I demonstrated here. The carriers will move from one side to the other, right? So you can understand it from that perspective also. From p-type semiconductor, you have to think in terms of holes, not in terms of electrons then. But it does happen, right? Physically what happens is that electrons will have some electrons metal will have some electrons filled up to the Fermi level, and when a p-type semiconductor comes in contact, some electrons will either get shifted from the metal to electrons to the semiconductor, or vice versa, depending on again their work functions. So that thing will again play a role. It's only the work functions that's going to play a role primarily. Ideally it's only the work functions that play a role. Okay, but it does happen. As I was saying, Professor Naresh has a complete diagram in which he talks about p-type as well as n-type. All right, so I request you to just look at that. I didn't add this first of all to avoid the confusion, right? Just understand, just so that I can devote more time to only one picture, right? And secondly, obviously due to the lack of time, right? But if you still feel some difficulty, then you can write in the forum. That's the best suggestion that I can give you. Or secondly, if you need that, no, you need some personal time, as I've been sharing my email id, and yeah, again I'm sharing my email id, right, and my YouTube channel link also. If you want to visit it later, you can write to me if you still feel that okay, some part of this whole puzzle is not clear to you. You're most welcome to write to me. All right. It's okay, you can move ahead.
Yes, sir.
Okay, thank you, Parth. Right, so that was that. Yeah, so I was saying there are some expressions that are involved just to, because when you understand the physics or the how it's behaving, the carriers and the junctions, and we try to quantify them, because ultimately we want to make devices and it's good to have some numbers, which material to choose, etc. We'll see one question on that also, with how materials behave differently with different metals. All right, so these are some few expressions. All the quantities have been talked about: phi m, chi, phi s, you see them here. The only thing that new, that you kind of new, I should not say it new, is phi n. Just we are denoting it differently. So remember, phi n, remember, is nothing but EC minus EF. This is nothing. You have been seeing EC and EF throughout. Just a new way to write that. All right, nothing new. Phi b 0, you see this Fermi level has to be the same. So phi b 0 is nothing but your where is phi m? Just a second. Yeah, so phi m, right? This is the barrier that I was talking about. So phi m minus chi, this is the barrier that
Sir, that is divided by charge only, na?
which thing?
EC minus EF divided by charge.
So it will be EQN. Yeah, you're correct. So usually work functions we measure in voltage, and energies we measure in terms of electron volts energy, right? So hence this is multiplied by such. Thank you for pointing that out. I was saying that earlier, I forgot it myself. So the barrier, you see, for electron from to come from here to here, right? It has to rise up by phi b naught, E phi b naught. We're talking about energy here, and then it has to come down by chi. This is chi that we're talking about here. So hence, so different ways of writing it. So just these come into different, same thing, there's different ways of writing. It's a built-in potential. Built-in potential is nothing but you go up from here, you rise by phi b naught, and then this is the built-in potential. So you subtract this entity. You can VBI plus phi n is equal to phi b naught, which is written here, right? And this is the barrier. This is in fact, this is the most important metric that we try to figure out. All right, okay. So, and this is, as I was telling, treat it as a p plus n junction. So we saw that there's no xp involved here, and this expression, if you recall, is very close. In the bottom of the screen you see the step p or the abrupt pn junction. Just compare this expression with this expression. So when we have on the, just assume this, if this is p side, p plus side, what's going to happen? Na greater than nd, right? This is n side. Then we can ignore the Na term. The expression becomes 2 epsilon s over q vbi over nd. It's the same expression as this. So you go from here to here when Na is greater than nd. This is what I was saying, that all the understanding that you have of p plus n junctions, in terms of expressions I am talking about here, not in terms of the physics, right? Just in terms of expressions, it's easier to remember if you recall all your expressions for your p-n junctions. So this is just a cheat sheet for you. When we try to solve the problems, it becomes handy just to you refer to them, and we can get away with things. Okay, so now let's just use whatever understanding that we have. The physics and the mechanics of it we have seen. Now let's try to solve some problems. So question says copper is deposited on n-type silicon substrate to form an ideal Schottky diode. So what we are doing is, so let me draw the same picture as we are doing. So this is the semiconductor that we have, right? So this is the semiconductor, n-type semiconductor. What I am doing, I am depositing some copper. Copper is the metal copper, right? So what we have is a metal semiconductor interface, and all the phi m, chi, everything is given to us. We are required to find the phi b. That is the phi b denotes the potential, the Schottky barrier. Sorry, the same slide from the last. This is the same expression and picture from the last slide. So we saw that phi b 0. This height is nothing but the metal height, right, minus chi. This is what is referred to as phi b 0. So let's just put in the numbers. Phi m is given to us as 4.65 minus chi. Chi, remember, is the electron affinity that we have, and that would be 4.03. This comes out to be 0.62 eV, right? So this is 0.62 eV. fairly straightforward. Just you put in the mathematical expression, you put in the values in the mathematical expressions, and we get the answer. How we got them, we just I had just talked about in detail that how we got these terms. Secondly, what is a built-in potential? So again, as I've been always saying, if there is some depletion region, built-in potential and the electric field will be associated. All right, so here what is the built-in potential? So built-in potential, again here, since we have already find out phi b 0, right, so we can see phi b 0. If you deduct phi n from this, you'll get vbi, right? And how do we find yn? We just find out in the previous. So we know this is 0.62 volts. Sorry, did I say ev in the last? No, this is not. Wait 1 second. Okay, so everything is being given in terms of ev. So please be careful while using them, whether the units are in ev or in volts, right? So either use everything in ev or use everything in volts. So here everything was in ev, the answer was in ev. So let's stick to ev for now. So phi b was 0.62 ev. Okay, right, so this we know 0.62. Phi n we don't know. How to find phi n? Phi n we know is, just look at this region, use a different color. Look at this region. So what's going to happen is, what I have written is, this is nothing but Eg by 2. I'll draw this, I'll zoom in the diagram over here. So this is EC, this is EF, this is EI, and this is EV. This is what we are interested in finding out, phi n, right? So we know that the complete band gap, just let me erase this. So this blue region has been zoomed in. Okay, so we know that this complete thing is Eg, forbidden band gap, and this entity would be Eg by 2. This will also be Eg by 2, the intrinsic level, the half of it. So what's happening? So that's what I've written, phi n, this entity and this entity, EF minus EI, will be nothing but Eg by 2. Okay, so now you will ask how to find EF minus EI. We know that, just give me a second. So this will be Eg by 2. Eg is given 1.1, so 1.1 by 2 minus EF minus EI. Now how to find EF minus EI? I want you to recall the expression from the earlier sessions that we have done, right? EF minus EI, I'll write it here, EF minus EI is nothing but Ni KT ln, sorry, this is KT by Q, Nd by Ni. We have seen this expression multiple times. How high the EF minus EC is also there, so that will become Nd over Nc. This is the form that we have been seeing. This is KT by Q, right? So what's going to happen? Let me just put this EF minus EI expression. Sorry about that, just a second. So let me put this expression over here. So this will be KT by Q ln Nd over Ni. So 0.55 minus KT by Q is 26 MeV ln Nd is the doping on this N-type semiconductor, that's 10 to the 16, over Ni is your 10 to the 10. So this will come out to be ln of 10 to the power 6. So natural log of 10 to the 6. This is 13.81 times 26 MeV. So that's coming out to be 0.36. This will finally come out to be 0.19. 1 second. EV. Let me see that I'm not made any mistake. So KT by Q ln Nd over Ni, so that's 10 to the power 6 right? So 10 to the power 6 into exponential. So sorry, ln 10 to the 6, yeah, it's 13.81 times 26 MeV. So that's coming out to be 0.36, and you deduct 0.3 sorry so phi n is 0.19 ev, but we are required to find vbi. All right, so let me just go back to that expression which I write in black. So vbi will turn out to be phi b0 is 0.62 minus 0.19, so that will come out to be 0.43 ev. Not everything I have been doing in ev, so just be consistent. So 0.43 ev, the correct the closest option that we have is 0.42. So that's how we do this. So the only thing of note here is you just remember this, that how to find out the phi n or the ef minus ei. In fact, we know this from the earlier sessions that we had done that. Rest all the things, it's fairly simple to figure out. All right, now the third thing, now when we have zero applied voltage, this means we are at equilibrium. We need to find the depletion width. So you saw this formula, that how it's linked to the step p-n junction depletion width, and this is the picture that we have. So now we know everything in this expression, so I'll simply put the values twice of epsilon s. Actually here is epsilon naught also, so it's 8.85 10 to the power minus 14. Remember, yeah, the units have to be per centimeter square. Epsilon naught must be given, and it's 11.8 times vbi. If we recall, vbi was 0.42, so this is 0.42 ev, so e has to be there, divided by e times nd. Nd is given as 10 to the 16, so e and e do get cancelled, fortunately. So we solve this expression, just give me a minute, times 11.8 times 0.42, so that's coming out to be square root of 87. That's coming out to be, just a second, I made a mistake, twice of 8.85 times 11.8 times 0.42, right? So and then we take the square root of this fellow. Yeah, so it's coming out to be, in terms of it has to be centimeters, so it's coming out to be 0.23 into 10 to the minus 4. Put in all the values. There's a mistake somewhere, hold on. Yes, this is in volts. E and E won't get cancelled, this has to be volts, so it has to be 1.6 10 to the power minus 19. You put in the values, and the answer that comes out to be is 0.23 10 to the power minus 4, so minus 6 meters, so 0.23 microns, so 0.23, this one. So what I was saying a bit about earlier, that if this is thin enough, it can tunnel. We talked about that tunneling aspect. It's large, so converted should be around 234 nanometers. Tunneling probability will, if you tunneling probability for such high widths is very low. So the current that's going to be dominant here, right now the applied bias is 0, but if you do apply a forward bias, the current that's not going to be the tunneling current. That's what I meant to say. So tunneling is absent here, or I should not say absent, negligible. You'll always find some probability, but it's negligible here, right? So coming back to our problem, so we were given a copper and silicon Schottky diode with all these expressions and with all these numbers, sorry, and we had determined the expressions, and we just figured out that yes, there is some depletion weight, there's some built-in potential, just like we saw in the PN junction diodes, right? One more question, in fact a couple more questions on the same aspects. So now what we have is, we have now 3 diodes A, B and C formed an N type with their doping concentrations are different here, and the barrier height is given, right? So remember, barrier height is not determined by the doping per se, right? Barrier height is determined, if you recall the formula, which if you recall the formula, the barrier height is determined by the metal and the electron affinity. These are fundamental properties, these do not depend on the doping. So barrier height, hence you see, if you choose a specific metal and a specific semiconductor, barrier height is fixed ideally, right? So hence for all these 3 doping concentrations, the barrier height is fixed as 0.65 volts, right? But we are required to find the phi n. You recall again, this is the phi n that I was talking about, and this expression we had solved this earlier. So let me just write this in a way that we can understand. So Eg by 2 we know is 0.55 eV minus EF minus EI, if you recall, was 26 MeV times ln Nd over Ni. So this is what we had seen earlier. Now we just need to find for the 3 different dopings. So let's just solve for A. So phi n A will be 0.55. This is just a mathematical exercise now. 26 MeV times ln Nd is, for A is 10 to the power 15. 10 to the power 15. Ni is what's 1.5 into 10 to the power 10. So we'll just simply, I'll quickly plug the numbers. So it will be ln of 10 to the power 5 divided by 1.5 into 26 MeV. So that comes out to be around 0.29. So this is 0.55 minus 0.29 eV. So this is coming out to be around 0.26 eV. Now again you see the options are in volts. So due to depending on our convenience, we are someplace dropping electrons, somewhere we are reporting in terms of voltage, sometimes in EV. Just be careful, that's all I'm saying, okay, because the expressions are different. So we know phi n A we have determined, right? Now let's determine phi n B. So phi n B will be again 0.55 minus 26 MeV ln, this is 5 into 10 to the power 15 over 1.5 into 10 to the power 10. So that will turn out to be 0.55 minus, let's do this quickly again. So this will be ln 5 into 10 to the power 5 divided by 1.5 into 26 MeV. This turns out to be 0.33. So this is turning out to be 0.22 eV. Okay, now for the sake of completion, let me do C part also. So C part will come out to be 0.55 minus 26 MeV ln 10 to the power 16 over 1.5 10 to the power 10. This will be 0.55 minus, so this is ln 10 to the power 6, sorry, here 10 to the power 6 divided by 1.5 times 26 MeV. This is 0.35. This is turning out to be 0.20 volts or EV, right? So we have 0.26, 0.22 and 0.20. Let's do that. 0.26, 0.22, 0.20. This is the option. Fine, anyone can put in the numbers and give you the answers. What do we learn from this? So we see that as we are increasing the doping, you see the doping is being increased in this from A to C. If we increase the doping, right, so what's going to happen is that, and you expect that, right, if we increase the doping, then more number of electrons can jump from this side to this side, right? And correspondingly, what's going to happen, if you recall your VBI expression from PN junctions, it's inversely dependent on doping. Sorry, VBI is directly dependent on phi n is inversely dependent on, sorry, W is inversely dependent on doping, which is somewhere, yeah, W is inversely dependent on doping, right? So again you will see a similar thing that's going to play out here. So we did not find W, we just find out this fellow, and we see that as we increase the which you expect, essentially this phi n is nothing but closeness between EF and EC, right, between EF and EC. So as you increase the doping, this EF minus EC minus EF should reduce, because you are giving it more, you're doping it more and more, so EF will move closer to EC, and you see this keeps on decreasing. This EF minus EC gaps will keep on decreasing as you increase the doping, which we see in this case, right? Second part of it is when you try to identify the built-in potential, right? How to do that? This is the expression. Okay, again, what colors did I choose? Blue, green and black. Okay, so let's do that. So let's first solve for VBI-A. So VBI-A is 5B0. This barrier I told you will be fixed, because once you finalize the metal and semiconductor, this cannot change. So this has been given as 0.65 and phi n of A, which is 0.26, right? So 0.65 minus 0.26 is 0.39 eV, and second will be your VBI of B, right? For B, it's going to be VBI of B is again 0.65, sorry, minus B is 0.22, so it's 0.43 eV. And finally what we have is for C, and for C we have 0.65 minus 0.20, this 0.2 here, so 0.45 eV. You see the built-in potential is steadily increases as you increase the doping, right? So what we have is VBI C is larger than VBI B, and then VBI A, this one. Why is that happening? So you see this barrier is fixed. If you increase the doping, phi n will keep on reducing, right? And thus the barrier, the built-in potential will also reduce. It's a similar thing that we, if you recall in PN junctions, if you increase the doping, right, the built-in potential keeps on decreasing. Again, I remind you that the Schottky barrier is dependent only on the fundamental properties of the semiconductor and metal, which in this case is the work function. Again, this phi B0, I should remember phi m minus chi. So you have fixed this. The nature has given this to you. You cannot tinker with this. The only thing in your control is phi n, and you can change phi n by doping. So this is the beauty of semiconductors, which I've been telling you about, that you can change, you can tune the semiconductors based on your so for instance, someone wants 0.45 EV, then you can dope it 10 to the power 16. Someone wants 0.439 EV of built-in potential, they can dope them in 10 to the power 15 cm minus 3, right? So this has some practical. This is not just for the sake of numericals that we are doing. Based on how much built-in voltage you want, how much depletion width you want, all these dopings are determined, all right, based on the requirements. Okay, so I think this is the last question, so to speak, from this junctions part that we have, right? The built-in potential, the mathematical expressions that we saw just now. Okay, so let me quickly complete this. So this figure shows you the barrier height, right, for gallium arsenide and silicon. So this is for black is for gallium arsenide, blue is for silicon, and then the x-axis you have the metal work function, right? What we are required to find is the work function of gallium arsenide in terms of gallium arsenide. So we are making a metal semiconductor junction between gallium arsenide and gold. So let's do that. So and so for if we want to form a gold contact, this means we are somewhere here, right? This means this is the point that we are interested in, because here is gallium arsenide. So we call this, let's say, the barrier height. We will just assume that is given to us as this phi bn. This is the same expression that we had seen earlier, right? That phi b, the barrier is nothing but your or you can see it from here itself, right? So what's phi s is nothing but S stands for semiconductor. So in this case it's gallium arsenide, right? and this thing that we saw was nothing but phi n, same thing that's written here. So phi of gallium arsenide, this is what we are required to find. This should be equal to phi bn, which we see over here, 0.8 plus chi is being given as 4.07, so it turns out to be 4.87 eV. Okay, now this yeah, so that's how we do it. All right, let me just confirm, just a second. Yeah, phi b is phi m minus chi, correct. Okay, so I guess that completes this part where we try to figure out where we play with the work functions and the metals and so on, and we figure out just a second, hold on. Phi barrier would be phi m minus chi. So phi barrier, if it's 0.8, phi metal is phi, should be chi. So chi minus 5, yeah, it's close enough, 4.2. So it's fine. I was just doing a cross check the values are correct or not. So it's 4.2 and 4.1. We have made some approximations, so the correct answer is 4.87. All right, so that is it from this part. Okay, right, so as I was saying that in so we'll take a pause till now. If you have any doubts, questions, comments, please you may ask, because from now we'll just do a couple of questions on the from the current. I have told you that there are some, these are devices which are used to carry current. We'll just see that how is the current being transferred, but before that I want to pause here for a bit, and yeah, so if you have any doubts you can ask, feel free to ask. Okay, if not then we'll go ahead. So on the top you have a p plus n junction diode, you can see that. So this is, and we saw that what excuse me, just a second. Yeah, so for a p plus n junction there will be much more larger quantity of holes as compared to the electrons. It's, you can just imagine there are much more number of holes. So what's going to happen, the current is going to be dominated by holes, hence you can call this as negligible. Similarly, we saw a similar picture. I told you that you can compare a metal semiconductor diode from to p plus n junction diode. Here again, if we but the difference is here the emission is thermionic. So here if you after equilibrium, if you disrupt it, that means you apply a bias. So so only the electrons will dominate in this case. Okay, similar to that, and these are the expressions that we have. JST is nothing but your reverse saturation current again, but this is slightly different. I told you because of thermionic emission. This is your Richardson constant. Again, refer to the I request you to refer to the slides or the textbook which Professor Naresh has referred for more details, and we will talk a bit about the dependence of temperature, I think, if we can, right? So let me see if I have expressions for them. No, I don't have. Okay, so so if you recall, for a junction diode, right, it was dependent on your diffusion constant. The for a PN junction was dependent on diffusion constant, and there are some dE mu, I'm forgetting the expression, but it was dependent. So d and mu again, they do not have as strong dependence on temperature as in, so this is by the way for a Schottky diode. So key difference between these reverse saturation constants for Schottky and PN junction is the temperature dependence. Here the temperature dependence is polynomial, right? It's very strong. So when you operate at higher temperatures, you see much higher leakage currents, in Schottky diodes as compared to PN junction diodes. This is one key difference. Second thing, I'll illustrate using this example. Okay, we have been given a PN junction diode and a Schottky diode have equal cross-sectional areas and have forward bias currents of 0.5 milliamps. Okay, so let me write this down somewhere. So their areas are similar, right? So I can J equal to I times A, sorry, I over A. So if their areas are similar, this means their current densities will also be similar because the forward current is same, right? So I say IPN equal to I Schottky and APN is also equal to A Schottky. So this implies JPN will be equal to J Schottky. So I equal to J by A. So the left side and the right side will come out to be the same. Alright, so the current densities will also be the same then. Okay. And the reverse saturation current, so you can see everything here has been given in terms of, not in terms of J but I. This means if the area is similar, J and I can interchange them, right? Because area will eventually get cancelled out. That's the message that I'm trying to give you. Okay, coincidentally it happens that the expression is the similar nature for both PN junctions as well as your Schottky junctions. Okay, so let me just write for JPN, this will be equal to JSPN, saturation current of PN, times exponential of E VPN over KT minus 1. Okay, another information is that forward bias voltage between two diodes is 0.3. See, if you recall the diagram, we saw that there's a D voltage of recall this diagram. So this is your Schottky, this one is PN. So for them to have the same current, right, the PN bias voltage has to be much higher. That is what's written here. So VPN minus V Schottky has been given to us as 0.3 volts. Okay, VPN minus V Schottky, because PN has to be biased higher for them to have the same current. This is I versus V. Alright, the second thing that I have is J Schottky is equal to reverse saturation of Schottky exponential of E V Schottky over KT minus 1. Let's divide them, right? JPN is equal to JSH, so your left side will, so I'll divide, this is 1, this is 2, let's do 1 divided by 2. So LHS will become 1, it will become JSPN over JS Schottky, and you have exponential of, so this upon this. So what's going to happen, I'll write it like this: VPN over KT minus 1 minus EV Schottky over KT minus 1, because exponential are in denominator, so they can be subtracted like this. So what you will get is that if 1 and 1 will get cancelled, right? So you will get JSPN equal to JS Schottky times exponential of EVPN minus EV Schottky over KT. This 1 and 1 will get cancelled and it will be left VPN minus VSH. This will be divided by, sorry. So now you put the values. JS has been given to us as 5 into 10 to the power minus 7 into, sorry, divide by exponential of, so KT by Q is 26 milli-electron volts and VPN minus V Schottky is given as 0.3. This will be 0.3 over 0.026 milli-electron volts. I'll just try to figure this, try to find this out using the calculator. Just give me a second. Exponential of 0.3 divided by 0.026, and that will be 5 divided by this figure. Okay, so it's coming out to be around 4.87 into 10 to the power minus 12. 4.87 into 10 to the power minus 12 units or whatever are this JS I have taken it as amperes. I'm ignoring the area, right? Because if you multiply by area, they are the same, they get cancelled also. So 4.87 10 to the power minus 12. So 4.87 10 to the power minus, this is the closest option. All right. So what do we notice? The reverse, let's say if both of these devices are in reverse bias now, what is the current in PN diode? PN diode will have something like 10 to the power minus 12 amps of current, picoamps of current, that is, right? What will be the current in Schottky diode in reverse bias? 10 to the power minus 7, that is your 500 nanoamps. There is a huge difference, 10 to the power 5 orders of difference between their reverse saturation currents, right? That's the key difference. So some, depending on their requirements, some place Schottky diode is used, some place some place PN diodes are used. So for instance, if you want to you must have heard about Zener diodes, right? They are operated, sometimes they're operated in their reverse bias modes as a voltage regulator. They are because we want to pass some current through them, right? Even in reverse bias, some current, but the voltage will remain clamped, right? Some place you want your devices to withstand, you don't want to leak more current in reverse bias. There you must use, you are advised to use rather the PN junction diodes, because Schottky diodes will have huge amount of leakage current. But if you want to have a better turn on, note Schottky has a much lower knee voltage, right? So if you want to have an earlier turn on, then it's advisable to use the Schottky diodes. So as I was saying, depending on your requirements, you choose different flavors of diodes, right? The properties are different, yes, but when you are designing a circuit or for a specific application, you only consider that, okay, I want forward current to be this much, I want turn on voltage to be this much, I want leakage current to be this much. You don't care about that, whether you want which device, you just care about their characteristics, the numbers, right? There's physics behind that, but when you talk about numbers, it's just that which one is advantageous. This understanding between Schottky and PN can help you. And also we also seen an ohmic contact, right, which is just V equal to IR simply. So there the current will be same, I mean not same, but it will increase linearly rather than the exponential thing that you see here. Okay, so yeah, that completes the Schottky junctions or the metal-semiconductor junctions. I'll take a pause here because before switching to what is a metal-oxide-semiconductor capacitor, just we'll first understand what, because you must have heard about the term MOSFET, but I'll take a pause here. If you have any doubts or comments, please feel free to ask or speak or write. All right then. We have around 25 minutes.
Sir?
Yeah.
Sir, in this question, it is given that the current is 0.5 ampere for both.
Yes.
But current will be different now.
Why?
Is it same current for PN junction and Schottky diode?
So that's why I have drawn this diagram. You see here, I will just make it in a different box for better clarity. See this blue box. What I have written here is that I have drawn the IV characteristics. X-axis you have voltage, y-axis you have current, and I have drawn the behavior of a Schottky diode and a PN junction diode. All right. We know a PN junction diode will turn on at some later time. So this current that you are seeing here is nothing but 0.5 milliamp. So this line is 0.5 milliamps. So I'll ask then, when does Schottky diode have 0.5 milliamps? You will say this voltage. Let's call this as VSC, V Schottky, correct? I'll ask, when does this PN junction diode has 0.5 milliamps? You'll say, okay, at this one, and let's call this VPN. Now you can clearly see VPN is greater than VSC, correct? VSC is this. correct? And VPN minus VSC has been given as 0.3 volts, which I have written here, correct?
Yes, sir.
Yeah. So this is the only information what was given in the problem. The only doubt that might arise is that is it VPN minus VSC 0.3 or VSC minus VPN that is 0.3, right? Those are genuine questions. But since we know a Schottky diode has a lower knee voltage as compared to a PN junction diode, right? Hence I could draw these characteristics, and from this I could conclude that it's indeed VPN minus V Schottky, not vice versa. All right.
Yes, sir.
Yeah. So that's how. So just that's why I was saying, just remembering these some very, I understand that you cannot remember the numbers apart from basic numbers like semiconductor band gap is 1.1, intrinsic concentration of silicon is 1.5 10 to the power 10 cm minus 3, but you cannot we cannot no one expects you to remember the actual numbers of their hundreds of thousands of things, but it's beneficial for you for your understanding and for even for solving problems that Schottky diode will have lower turn on or lower knee voltage as compared to a PN junction. A normal, I mean, an average Schottky diode will have a lower knee voltage than an average PN junction. That's what I meant to say. There are different flavors in which you can tinker with the turn on voltage and so on, but this is a general picture that I'm talking about, and rest is just fairly straightforward thing. That rest is just mathematics, and that happens because they both have the exponential dependence, though from different reasons. All right. Okay. So and any other comments or questions?
No, sir.
We have some time. Okay, then let's go ahead. So here we have a metal oxide semiconductor capacitor. MOS stands for metal. You see this dark this black thing as metal. This gray region you have is your insulator. So usually what we have semiconductor substrate. Let's assume this to be silicon. Okay, usually an oxide is SiO2. All right, this is an oxide, and silicon dioxide is a good insulator. So that's why this is called sometimes a metal oxide semiconductor. Metal you can have, we saw, depending on different metals you can have a Schottky contact or an ohmic contact, right? So this metal is of your choice, what kind of contact you want to make. That was in Schottky, remember, but some properties of metal will still hold true here. Electron transport naturally cannot happen. We'll see why. So so this is the oxide. By the way, this sometimes is also referred to as MIS. M stands for metal, I stands for insulator, S stands for semiconductor. So just it's virtually the same thing. If insulator happens to be oxide, which is more often than not for silicon semiconductors, it becomes a MOS, metal oxide semiconductor. It's a capacitor. Why it's a capacitor we'll see in a little bit, but I'm just explaining this term, right? How it behaves as capacitor we'll see. Okay, just before, even if I do that, so capacitor, please recall your capacitor. It's something like this, a simple parallel bit capacitor. So here we have, this is filled with some dielectric. It can be an oxide. For our purposes we'll assume to be an oxide, and SiO2, and it has two metal plates. Here please recall we don't have two metal plates. This is left side is plate 1, this is plate 2, this is a capacitor filled with some dielectric. So this is plate 1, this thing somewhere here will be your plate 2, maybe here, I don't know, or maybe this is plate 2. We'll see where is second plate, but it's a capacitor. You can see dielectric is there and one metal plate is there. We just need to figure out where's the second metal plate. Metal plate is there to hold charge. Okay, so if we can somehow find some charge in the semiconductor substrate, right, then it will behave similar to a capacitor, and it's called a MOS capacitor because it has these three different materials, right? There are some basic assumptions for an ideal capacitor, like we have been talking about to start with, it's better to assume it ideal, and as we progress, as you mature in this field, you'll see that bit by bit all these assumptions you will tend to violate. All these assumptions you'll tend to violate a little bit. Okay. So metal semiconductor Fermi levels are same. So we'll see when we see the Venn diagram what do we mean by that. Second is no traps at semiconductor oxide interface and within the oxide. So this oxide, when you are depositing or creating, it can have some impurities, right? Or it can have some traps, where essentially traps are usually, more often than not, traps are usually non-idealities. So hence we are assuming that this is a perfect oxide. Okay, so there are no traps inside or at the interface, at this interface, at the oxide and metal. So I'll draw in a different color, green color. So what is this interface I'm talking about? This interface, where oxide and metal meet. So we're assuming this to be an ideal interface. Okay. Third thing is metal is thick enough to be equipotential. That's important, because we want, just like it's like an infinite parallel plate capacitor, which you have, I hope you have studied in your I don't know, senior secondaries, or maybe in your first year also, right? So this is thick enough to be equipotential. Fourth is semiconductor thickness is larger than the maximum depletion region thickness. Okay, we have solved a problem. So when you apply an electric field here, right, this gray thing that you see is actually the depletion region, which you'll see. Depletion region has this total thickness T silicon, right, and this is a depletion. Let's call this W. So what we are saying here is that T silicon is much larger than W, which is usually the case. This is, substrates are a few tens of or even hundreds of microns thick, right? And this depletion widths, if you recall, are it can go to a few microns, but not more than that. So usually this assumption is more or than satisfied. We are safe here for this. And oxide is a perfect insulator, again, that it cannot conduct essentially. So oxide, you see that there are many considerations we are imposing on oxide. Oxide has to be perfect, this means, and there should be no traps. So this becomes very important, the quality of the oxide that we are depositing or growing here. It's in fact, it's one of the most important things in the MOSFETs that we'll eventually study, right? But this is the basics of a MOS structure, and how it behaves as a capacitor we'll see right now. But just this is some very basic definitions that, so you can speak of that. What we have is, we have to choose the correct statements here. But let me just illustrate what I'm talking about here. So this is again your similar, this is your metal, this is your oxide, and this is your semiconductor. So this is an MOS structure, right? So what do we have here is that, so this is your EF, this is your EV. EF is, and this is your EI, the dark black. EF is close to EV, right? It's and EI is when you have intrinsic. So this means this is a p-type semiconductor. So I'll write it as p-type. All right. So now if I want you to recall some expressions. So remember, there are some expressions like N equal to Ni exponential of EF minus EI over KT. This is from your, I think, second or third session. And similarly, you can have P equal to Ni exponential of this will be EF minus EF minus EV over KT. I mean, these are for 1 second, let me just be clear. Sorry, this must be EI. There will be negative sign, so it should be EI minus EF. I'm not writing this so that I'll get confused, and that then there's a risk of me confusing you. So let's just stick to the electrons concentration. The same picture is true for holes as well. All right. So this is the expression that we have. This is true for when we have flat band, EF flat band, which we see here. So this is so EF is constant, we are in equilibrium, so we can apply this. What notice that, by the way, this is a p-type semiconductor, but this gives rise to what is known as NMOS, because what's happening here is, you see in this region over here, EF is closer to EC, right? And we know if EF moves towards EC, this means we have an N-type behavior. But this was a p-type bulk. This bulk is p-type. So this complete region is bulk p-type, but just at the interface, EF somehow has moved closer to EC. This is EC, and thus this only at the interface, right? This material, this architecture, this kind of structure will behave as if this is rich in electrons just at the interface over here. These electrons cannot go inside oxide. Please remember that we told you it's a perfect oxide, right? So this is one of the things. Now what we have charge over this. So let me draw this picture again. This is one plate of the capacitor. This is your dielectric oxide, and this is the second plate, this thing. I will draw in a different color. Just give me a second. So over this region over here, so what's going to happen is, I can represent this by something like this. There are electrons here, they are trapped, they are just stuck at this boundary. So this structure is behaving something like this. This is the VG that I've applied here, and this is the oxide. This is the second plate. So what we have a capacitor, right? That's how a capacitor behaves. Two plates which have charge, which can store charges on them, and in between is in this case it's a perfect dielectric, right? So what it has electrons here in the semiconductor, although it's bulk p-type, but just at this oxide in semiconductor surface we have electrons, and such kind of a device is called an NMOS. This is called inversion charge. We'll see, just give me a minute. This type of architecture is called NMOS because the electrons are here. So what we'll have is, so NMOS, just a second, I hope I'm not making a mistake. So this I'm sure is an so this is rich in electrons, but I'm forgetting the nomenclature. Can anyone help here? Is this PMOS or NMOS? Anyone? It's done in the lecture slides. I tend to confuse a bit among these things. So can anyone help? Is it PMOS or NMOS? The structure on the left. Come on. This is a fairly straightforward question. I know I've forgotten. All right. PMOS will have, so this thing that you are seeing here, this is called the body. You'll see I was not bringing this up because it might get too complex. This is called a body, this thing, the bulk that we are seeing, right? So if the body is p-type, it will have NMOS. So we'll have that NMOS devices will have electrons as inversion charge. Similarly, this is a p-type. You can see this is this is a n-type semiconductor because EF is close to EC, and this will have holes. So you can see that the EF is closer to EV here, so this will have holes as inversion charge. All right, so that's how we do that. So PMOS will have holes as, where is that? Yeah, PMOS will have holes as inversion charge. See, by default, the bulk region or the body region will have excess of, let's consider only the left side. P-type will have excess of holes, right? But only at the interface will have access of electrons due to this some peculiar thing that's happening to the application of VG, which we'll see right now. How does a MOSCAP operate? So first you have VG equal to 0, right? Nothing is happening. You have, so this is EV, all right? So please note that I'm taking a P-type semiconductor. This is a P-type body or P-type semiconductor. Okay, because EF is closer to EV and nothing is happening, so this will behave exactly like this. And please note the first assumption that metal and semiconductor have the same Fermi level. So metal's level is somewhere over here, which is not drawn, right? So remember we had an metal semiconductor Fermi levels are same. Okay, so this is the Fermi level here. So Fermi level is flat throughout. There's nothing happening. Very good. Now, if I apply slight negative potential, right? Apply slight negative potential. So what's going to happen is that, think in terms of what's going to happen. There will be electric field that will be penetrating here. What's happening is that this will repel the holes away. Sorry, it's a negative potential, yeah. So it will attract the holes. The negative potential will attract the holes, and thus you see the bands, right? The band upward. Now EF minus EV just at the interface has become even smaller. This means the concentration of holes will be even more here. So the holes which are present in this bulk region, in the body region, will now get attracted to this. So what's going to happen is, right? So since we have this VG negative, so you will see on this interface, you will have excess holes. Here there are also holes. The holes are equal to Na, the background doping, whatever is there, but here is excess holes as compared to Na. Remember, this goes as exponential, right? This is called accumulation. This means you have accumulated the holes on this region. All right. Interesting things happens when you increase the voltage. So what's going to happen if you now apply positive voltage, you will repel the holes away from this. Compare first and third diagram, flatband and depletion. When you repel the holes away, so holes will leave behind a negative charge. So holes will get repelled away, so they will leave behind a negative charge. So how will the charge profile will look like? Let me draw the charge profile here. Just a second. So I'll draw the charge profile from here. This is Q versus X, let's say. It will be negative, something like this in the depletion region. Again, we'll assume the depletion approximation. So there will be some negative charge that is stored here. So what will happen if we keep increasing this voltage, right? Now, what's going to happen is something you can see now that this EF is now close to EI. This means although the bulk is P, at the interface, it's behaving like an intrinsic semiconductor. Concentration of electrons is equal to concentration of holes. This is the depletion. If you increase the bias further, the positive side, this bend will bend even further. And what you can see here is that that EF is now closer to EC. This means at the interface, it's behaving as if it's an N-type. This is an inversion from P-type in bulk. This has now been converted to N-type at interface, right? This is what we call an inversion. We expect P-type, we expect excess holes, but it's not happening. It's the excess electrons. This is a very thin charge. So if I try to depict this same picture over here, Q versus X. So you have some wider depletion region, because naturally you have extended the bias, so you can see depletion region between depletion and inversion. Depletion region is more there, but what also is there is something like this. In blue, what I will show is a thin sheet of charge of electrons. And again, why we call this capacitor? See, one is this metal, and second is this electrons, and in between you have oxide. This is why it's called a capacitor, because now you have essentially two two sheets. This is very thin, by the way, where that this is only at the interface. So at these two interfaces, it's like it's a parallel plate capacitor. That's the inversion. So in this we'll just we have run out of time, but we'll just try to identify which one is which one. Okay, so let's try to do that. So in the first diagram, we need to identify the type of substrate. So type of substrate we can clearly see is that EF in the first diagram, this is EF, this is EV. EF is close to EV in bulk, so this must be the P type, right? So this must be P type, so this cannot be correct, this cannot be correct. And this is EC, sorry, this is EF, this is EC, again this is EF, and this is EV. So this is P type, this is N type. EF is close to EC, remember that. So P and P, so we have P and P, and but we have noticed that if the substrate is P type, the transistor that we call is the NMOS, because in inversion, in case of inversion, you will see a sheet of charge that's happening here. All right, so we have P type, N type, and P type, so this option cannot be correct. And then okay, so which is left? P type will have NMOS, N type will have PMOS, so this is the correct option, this one. Sorry, not this. P type will have this is also wrong, this one. P type will have NMOS, N type will have PMOS, P type will have NMOS. This is determined only when during the inversion, so please not during accumulation. So that's how we define, that's how we name them. It might cause some confusion, but remember the name to MOS is given by its inversion charge, right? So P type, its inversion is N, hence it's called NMOS, which we also, I told you something similar like this. For P type, since inversion, it will be electrons here, hence this is called NMOS. So NMOS will have electrons as inversion charge, that's why. Okay, so now we need to identify that what is the gate voltage that we have applied. So remember, this is not flat band, none of them are flat band. Let's try to see this. So we have this EF and this is EV. What has happened that EF has moved closer to EV. This means the hole's concentration has increased at the interface. This is a P type, remember. So P type, how can you increase the hole concentration? If you apply a negative bias. This means why? If you apply a negative bias, the holes will get attracted over here and they'll accumulate on this side of the oxide interface. So what we have done is that we have a negative and we have accumulation. So this is incorrect. So actually this option is correct, negative and accumulation, right? But let's analyze the other ones. So this is an N type semiconductor in the bulk, right? So what's happening is that something like this is happening, that at the interface it's becoming even more N type. You see EC minus EF has become even more closer to EC, right? That means more electrons are coming here from an N type. That will happen when you apply a positive bias. When you apply positive bias, the electrons which are in the bulk will get attracted to this interface, right? And that is again accumulation, right? Because you are just accumulating whatever the electrons that are present here. So this is again positive and accumulation, right? Accumulation means you're accumulating whatever there is present in the body. You're not inverting anything. It's N type is accumulating, fine, that happens. What's happening here? So this is a P type, right? This is P type. At the interface you see that, so this is the depletion region, this thing. So at the interface you see EF is close to EC than to EV. This means at the interface it's behaving like an N type, but bulk is P type. What is happening? This is known as inversion. So inversion is happening, and we know inversion can only happen when you have a positive polarity here. So positive polarity, because holes will get repelled. You increase the bias, they'll keep on getting repelled. You first enter depletion and then eventually you will enter the inversion, right? So hence this is the correct thing. Okay, so that's how you just try to identify them. We are not going to mathematics right now, just trying to identify them. Quickly we'll do the other thing. So again we'll try to identify the substrate first. So substrate here is, so this is EF is close to EV in the bulk. This is a P type. So P type will give rise to NMOS again, right? So this is p type, and it can result in an NMOS capacitor. This is an n type. You see EF is close to EC in the bulk, so this is n type. This is again an n type. So p and n and p type, so p and n and p type will give rise to NMOS, and so this is the correct option: p type NMOS, n type PMOS, n type PMOS. Similar to the last question. Again, we'll try to identify what's happening here. So this is p type in the bulk, but remember, at the interface what's happening? It's intrinsic. When will it become intrinsic? This means all the holes that are here have been vanished. That happens is, this is called the perfect depletion, because EF is directly equal to EI. This means it's behaving like an intrinsic semiconductor, but it's in depletion regime because all the excess holes that are here, right? You can see excess holes are here because this is p type. They have vanished. They have been. This means a depletion region has been formed. And when will this happen? When you apply positive bias, because positive bias will repel these holes, right? And it will form a depletion. It will get rid of all the holes which are excess, the holes which are due to the impurities that have been doped. This is n type, right? In this n type you can see that, but on this interface you see it's become p type because EF is closer to EV. This is EV, this is EC. This red line you see is EF. EF is closer to EV than to EC. Okay. Bulk is n type, but at the interface it's hole rich. What has happened? This is nothing but an inversion, right? This is an inversion. And when will this happen? This will happen. This is, remember, the body is n type. If you apply negative potential, you keep on applying negative potential, you will keep on repelling away the holes. Eventually depletion will come, and finally you will reach a state of inversion. This is again very similar to the first thing, just that this is n type. So bulk is n type, right? But at the interface you see now it has become intrinsic. This means all the excess electrons that are there, they have vanished. It's just intrinsic concentration that is there. What we have, you have depleted this region of the majority charge carriers, just electrons in this case, right? So what we have is depleted of charge carriers. Hence this is depletion. When will this happen? Negative bias, because you have to repel away the electrons. So this is negative depletion and negative inversion. This is the way we identify them. So the more you practice, the more you look at them, just try to identify. Just try to look at what's happening in the bulk and what's happening at the interface, and that will give you the complete picture, whether it's p type, n type, whatever. Just look at the bulk, look at the interface, that will give you the answers. Okay, so we are a bit over time, sorry about that. I'll stay back as always. If you have any comments, doubts, questions regarding this session, some feedback you want to give, I go too fast, too slow, too boring, you're more than welcome to hear and answer your doubts and receive my feedback.